new stuff. I think that's all we needed to do. So for incompressible flow, we're good with conservation of mass, conservation of momentum. For high-speed flow, we have an extra unknown, and that's density, because density can change. And so we need another equation. And we do have ideal gas, but then that introduces another unknown temperature along the way. So we still need another equation. And right now we have conservation of mass. And again, this is for one-dimensional steady flow, but it relates these variables to the variables at spot 1 to spot 2. And then we have the momentum equation, which tells us how pressure changes related to velocity. And that's the one that if we assume incompressible, then we get Bernoulli. But if we don't have incompressible flow, then the density changes and we need another equation. So we're going to use that one, and then we need conservation of energy. And the main reason that this equation comes into play is if you have high-speed flow, so flow going really fast, and let's say we run it through a duct where it slows down, so the velocity is going down because the area is going up, conservation of mass. When that flow slows down, we get high pressures. Right? Remember, when the velocity is going down, the pressure has to be going up because that's the force that slows the flow down. We get high pressures, and those high pressures can lead to density changes. Remember, that's the whole deal behind incompressible versus compressible flow. If you don't have high pressures to squeeze the air, you're not going to get a density change. That's why we said water is incompressible even at high speeds, is because it does not compress even with high pressures. But for air, for a gas, you get high speed flow, it's slowed down, you get high pressure, and so you get density changes. And so we need to relate P, and rho, not just with the ideal gas, but we need the conservation of energy. So this requires thermodynamics. Because thermodynamics is moving or changing energy. Thermal energy. And the conservation of mass, the momentum equation, this is dynamics. This is moving masses. So that's moving energy, this is moving masses, and that's just basic dynamics. And then aerodynamics is named that way because it's moving air. So aerodynamics is moving masses, aerodynamics is moving air, thermodynamics is moving thermos, or moving temperature energy. And that's the first law of thermodynamics, is conservation of energy. So we have to remind ourselves of some terms in thermo. You guys are taking thermo now or have had thermo, right? So this is actually going to be easier than a lot of the stuff you do in thermodynamics. So here we have a system of gas molecules. And we say the system is contained within a flexible boundary. And we talk about the internal energy. In the system, and it's internal energy per unit mass. Just like density is mass per unit volume, or specific volume is volume per unit mass, we don't have a chunk of stuff. We say, okay, we want to do it per unit mass. And this is the energy of random motion of the molecules. So that's all the molecules moving around randomly. If there's ordered motion of this, if that whole system were to move to the left, that would be dynamics. But we're looking at the random motion as what we sense as temperature. So it's the energy per unit mass. And the first law of thermal says E can change due to two things. And the change is dE. So E is internal energy, dE is a small change in internal energy. And you can get a change in energy due to heat transfer in. And here, in is positive. So obviously heat coming in is going to raise the temperature. And that's called del Q. So it's a small change in energy. And it's per unit mass, just like everything else. And then we can do work on the system. In other words, we can push on the boundary, squeeze the molecules together. Temperature, density, pressure are going to change, and that's called work. And it's done into is positive. So if we push and squeeze it, and this is per unit mass. All right, so we can change the energy by putting heat or by pushing on the system. And that gives us the first law of thermal, or the energy equation, that says putting heat in and doing work on the system changes the internal energy. This is the first law. It's the conservation of energy. So in this class and most fluids, that's what this is called. Conservation of thermal energy. That's different than the conservation of potential and kinetic energy for dynamics that we talked about before. This is the motion of the molecule. All right, so we look at this, and I don't see pressure, I don't see temperature, I don't see density. These are all our fluid variables. So at this point, it's like this is totally useless. But fortunately, we can put these terms in terms of the fluid variable. So that's what's next. The first one we're going to work on is the work. And the work is going to be in terms of pressure because work is force times distance, and pressure is our force. So this applies to any kind of force times distance of our fluid, but I think a piston is the easiest way to see how this works. So imagine a container here. So now I'm making the wall here rigid, but the piston here can move. And here we have a pressure, and so we're going to have a force on the piston. And if we allow it to move, if that force moves a distance ds, then that's our work. And that's work out. It's the system doing work out, so that's the opposite of work in, so that's going to be negative. So pressure, the cross-sectional area here, is how we're going to get our force. So pressure times area gives you the force. And then the distance is that ds. And so we're doing a small work over a small distance. So that's going to give us our differential work. And remember, this is per unit mass. Because that's how work is defined. So here's force times distance per unit mass. And if we arrange this, area times distance gives us a change in volume. And so what we have is a change in volume per unit mass. But volume per unit mass is specific volume. Which is volume per unit mass. And so this is a change in volume per unit mass. So we need to write this as del V, because it's the change in the volume per unit mass. And we remember that this is just 1 over the density, because density is mass per unit volume. And in fact, it's this reason why thermodynamicists use specific volume rather than density often. It's because in this work equation, you have 1 over rho instead of rho. So they just call that specific volume. And the units work out on this thing. So we're saying the change in work is P del V and pressure, this is newtons per meter squared. This is meters to the third. So that's volume per unit mass. And so we get a Newton meter. 2 of the meters cancel out per kilogram. So that's a joule per kilogram, which is energy or work per unit mass. All right, so that gives us the work in terms of pressure in the energy equation. It's just force, which is pressure, times distance, which then the distance is related to mass, or sorry, change in volume, because if you change the volume, you get that distance change. Oh, we need a minus here. Remember that? Because it's work out. I lost my minus sign. All right, so flip it around. Put that on the other side. Then you get the first law for gases. So far, so good, right? And then the thermodynamicists have found that often you measure this combination of variables. You measure energy plus pressure times specific volume. So they just say, let's call this thing enthalpy. I'll write it the other way around. Which always bugs me because there's nothing you can think about or look at, as far as I know, that is enthalpy in a system. It's not intuitive. But because these variables show up together all the time in the work, they say, let's define this H as E plus PV. And then the differentials, because we have dE and dV, we get so I just use the chain rule there. And I don't know why I started writing del, that's just D. And that's D up here is in there as well. So we can substitute. Here we got PdV and dE. So if you substitute up here, you can get the first law instead of in terms of energy, you can do it in terms of enthalpy. And so you get the heat transfer is dH minus ddt. So both of these are the first law for gases. One is in terms of the internal energy E, and the other one's in terms of the enthalpy H. All right, so this is a lot of theory in thermo, right? It makes sense because we said, well, conservation of energy is work plus heat going in gives us change in energy. And we've talked about this, but this internal energy is directly related to temperature. So what this is saying is that if we can calculate the heat in and the work in, we can tell how much the temperature is going to change. And then we can use the ideal gas law to tell us how much the density is going to change. So dE is related to temperature, and then we can use ideal gas to get density. And that's the whole goal here, is we needed another equation. So the chemist and the thermodynamicists have found out what this relationship is. So a change in temperature times this constant gives you a change in energy. And a change in temperature times a different constant gives you a change in enthalpy. And this is the formula that motivated, I think, defining enthalpy for real. And these constants are specific heat. If you remember from chemistry, specific heat is how much energy do you have to add to raise the temperature a degree per unit mass. That's all specific heat is. I remember doing an experiment where we had a chunk of, and we put a flame on it and we measured the temperature and then calculated how much heat went in. We got the specific heat. For solids, both of these numbers are the same. For gases, it depends upon how you heat up the gas as to which relationship is true. And so you get this is called the constant volume specific heat, which means you trapped your gas in a solid container and you heated it up. And so you get a different change in energy related to the temperature. But if you put it in a flexible balloon and heat it up, you maintain a constant pressure, which means you allow it to expand as it heats up. You get a different specific heat. And don't ask me why, because I don't understand it beyond that. I'm not a molecular chemist that can explain why these gases and how they behave in the atomic and bonding forces between them cause these two different things to happen. But experimentally, it does happen like that. But we're going to use these results, and we can put these in these equations of dH and dE. And now we've got temperature and pressure. We've got our fluid variables in here. And then we throw in ideal gas and we're good. All right, how are we doing on time? Okay. So we need to do some definitions about how most gases behave in flow around airplanes. So hold on to these equations. We're going to need this one and these. And we're going to do the substitution. But we need to talk a little bit about the heat transfer, because that's another part of the equation. So we have relationships about heat going in and how temperature changes related to energy. Fortunately for airflow, most of the time we have no heat transfer, because there's nothing putting heat into the air. So forget the engines, right? We're talking about flow over an airplane wing. The flow goes over the wing. There's not a burner heating up the air. There's no hot surface to transfer heat to the air. It's just the air flowing from this point to this point. And if there's no heat transfer, we say it's an adiabatic process. And that makes things a lot easier than if we have to deal with heat transfer coming in, because we're going to set del Q to 0. Obviously, if we can knock a formula or part of a formula out and set it to 0, we're good. Now, this obviously is not going to apply to air going into an engine where there's combustion, and then that combustion energy is heat transferred to the air. That's a whole different deal where you have to include this. But for what we're talking about, flow around the wing or around an airplane, it's an adiabatic process. And then the other big deal that you've learned in thermal is if you can assume a reversible process, that like there's no loss of order, and we can say that because we're not near a surface where there's friction. Friction is an irreversible process. because friction slows something down, but you can't reclaim that energy to speed it back up. It just turns into heat. So we're going to say that we have a no friction reversible process, so we're far from surfaces. And far is a loose term. It means that you're not really close to the surface where you're getting the friction effects. And so if you combine both of these from thermodynamics, you remember that's called isentropic. And that's the kind of flow that we have that we're going to study. And it's the reason that this is easier than if you take a class in friction flow, where the equations are a lot more complicated. So we can say adiabatic, no heat added, that knocks that out. It's a reversible process, no friction. There's no viscosity. And so then we can take the equations and put them together. We're going to knock the heat transfer out and then combine them together to get some equations we can use. Notice that just because we said there's no heat transfer does not mean the temperature is constant. It just means that there's no heat added, but if the air expands, even just due to ideal gas, we know the temperature is going to go down, right? So air can expand, the temperature can go down, the density can go down, pressure can go up and down. So temperature is not constant. It just means we aren't adding any extra heat so the energy doesn't change through the heat, it changes through the expansion and contraction. All right, so let's stop here because this is a good stopping point. And next time we'll start with those two equations and those relationships over there, and we'll come up with the energy equation that we have to use for faster speed flow. So things get more complicated, but they're also, in some ways, more fun and interesting because of what happens in high-speed flow when you get near the speed of sound. We know that because in the past, people have studied higher and higher speed flow, and they found out that stuff happens in flow as it gets near the speed of sound. So we'll also talk about what is the speed of sound. That's the sound of pressure waves in the air. Pressure is a fluid variable, so we'll actually use pressure waves to be able to calculate the speed of sound at a certain altitude. Excuse me. Along the way, we'll talk about people setting the land speed record, where people were building cars that went faster and faster, and they started to have to include the effects of high-speed flow in what they were doing. We'll also watch a video about breaking the sound barrier. So I'm going to start working those into the lectures. Probably watch part of the video every time we meet to get caught up on that. And then we'll talk about Mach number, which is how fast you're going relative to the speed of sound. Talk about shock waves and other interesting things that happen. So let's call it good for today. Everybody have a good weekend. It's supposed to be warmer. So get out and enjoy the sun. Any questions about Monday? Quiz is happening. Homework. Oh, I need to mention one more thing. Glad we have a little extra time. You guys are uploading your homework to Blackboard in PDFs, and everybody did a great job with that. I noticed that some of the files, when I click on them in Blackboard, I see them immediately inside of Blackboard. And sometimes it just shows a PDF file, and I have to click on it and download it to edit it and grade it. So I called Blackboard Help, and they think that it's related to which browser you use when you upload. It drives me nuts, because different systems in WSU, some stuff works better in Chrome, some works better in Internet Explorer. So I wanted to, hopefully, we can debug this. So I'm going to read off some names. If you're here, shout out, because I'm not singling you out. Everybody did this correctly. But Bruno, or Iverson, or Lamb, or Landel, or Mule. Any of you guys here? Checking out. Pierce, White. Do you remember which browser you used when you uploaded your file? Which app is that? The Blackboard app? So it's not in a browser at all. And when you upload it, so you go in there and you just go to the assignment and you do complete assignment, and then you attach the file. That should work. But you're using the app. Sahami, are you here? How about Turner? These are all people where I had to click on it to edit the file, and I'm trying to figure out what the difference is between. So all you guys here, how did you upload? So you use Chrome, because he's saying Chrome's one of the good ones. Chrome. Safari is one he said didn't work, but what's your name? Angel, I didn't have problems. What's your last name? Yeah, no, I didn't have any problems with that. No, I get it. I use Safari all the time on the Mac. I'm not pointing fingers here. I'm just trying to figure out how we can make it so it's easier for me to edit the files. So it sounds like Safari works okay. What did you guys use? Chrome and Chrome. So it sounds like Chrome and Safari work. Why the app doesn't work is crazy. You're using directly into Blackboard. When you guys submit, you go to the assignment and you do the completion of the assignment. I don't see that side of it, so that's why I'm asking. What do you do when you just say, I want to complete the assignment, and then you attach the file? Yeah. And then you're good, right? And that's what you do in the app, or is there another step that you have to do? So you get into it just like they did, into the complete assignment, and then you add content. Is that the same thing you guys see? Yeah. No, it will tell me. It's often it will say provided by Cam Scanner in it, and that works fine. And some of them that I can't edit inside say Cam Scanner, and some of them that like yours that I can edit say Cam Scanner. So I don't think that's the issue. It's interesting. I need to call Blackboard Help and say why, when you're using the app, go ahead and continue to use the app if that's easier for you. I'm just trying to figure out what's causing the differences in the files. Yeah, and so in Blackboard, when I go, like if you submit electronically, I can just go into the gradebook and I go assignment to assignment. So if I click on your name and your assignment, it opens it up and it shows me the PDF already edited. Like it opens it up in an internal editor in Blackboard. But for some of the people, it doesn't do that. It just shows the PDF file, and I have to click on the PDF file, which opens it in an Adobe. And then I have to grade it and then save it to the desktop and then upload that to your Blackboard again. Which is not a huge deal. It just would save me some steps so we can figure this out. Yeah, give it a shot, because I'll give you guys a multiple attempts. Keep track of which one you do, like make attempt 1, write down that's Chrome, attempt 2 Safari, attempt 3. Because that's strange, especially with the Blackboard app. What phone? iOS or? Yeah, okay. All right, thanks for the feedback. I'll let you guys go. If you guys are listening online, if you can use Chrome, that seems to work successfully. Although it seemed like Safari is fine as well.